welcome back to Andrew's Academy. We're going to start this 10-part series with a little bit of a prelude or background, whichever one you prefer, of the natural number. Because we know that the natural number, or you will learn that the natural number, holds magnificent properties when taking derivatives. So this natural number, right, if we write it out, this natural number is often referred to as e. Okay? And this natural number was discovered by Mr. Euler. And he was a Swiss mathematician in the 1700s who discovered this number. And it would ultimately change the game of taking derivatives of exponentials. So he, like all Swiss mathematicians surely do, was playing around one day and he graphed, let's just say, this is the original so that we can stay consistent with our colors. Okay, so he graphed 2 to the power of x, which is probably one of the most popular functions that exponential functions that you'll deal with in high school or whatever it may be because of its simplicity, right? So he took this, right, and then after he took the derivative. So if we take all the slopes, right, slope, point, slope, 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 and you put it together, let's change this to blue, right? You can see how it's going to almost be the same shape, right? This is just going to be the derivative. So he kept on going because, right, he didn't get disappointed. He kept on trying. So he went along and he graphed, let me stay consistent with my colors, 3 to the power of x, okay? And we know that changing the base to a greater number will increase the speed at which there's this exponential growth, right? So he took the derivative, right? And this derivative, much like here, right? But only ended up on the left side of the original graph. And he said, well, that's very strange. So he tinkered around a little bit and discovered that there was a certain point, which is known as the natural number, or E, or Euler's number, in which, let me draw this out, in which, right, if we take the original and we take the derivative, you can probably see where this is going by now, it gives you the same value, right? And this was known as e to the power of x, and e is approximately equal to 2.718. So this holds tremendous potential for taking derivatives of exponential functions because we know, right, if we just clarify this in mathematical terms, if we take the derivative of e to the power of x, which is just here, right? We proved that the original was pink. If we take the original in respect to x, our variable, all we're going to get is e to the power of x, right? Thank you very much for joining me in this video. I hope you enjoyed it and stay tuned for more. Peace.